Today we're continuing with day 16. We just solved day 15, and very fast recap for people that are new to this channel. We're solving all the problems using ChatGPT version GPT 3.5, 4, also OpenAI API. I have access to GPT-4 and using Bing as our searching engine and asking for some snippets, and we haven't yet used other tools, but we might use in some moment Dragonfly or Sage or Quody, and we are solving the problems using Go. Each part for each day we have actually two folders, one for part 1, one for part 2. We have a very simple structure. Input file, that's our final input that we need to solve the problem with. We have test input, some sample input from the problem description, usually to test the program, our program, and all the prompts that we had used so far, and we are specifying with which model whenever we use it as with Bing or GPT 3.5, GPT-4, and we have always a comma with the double dots, and after that the response that we have gotten for the given task. Let's copy our day 15 and simply make a folder that's day 16. Here we delete our input, we delete our text, and save them. We delete our program as well, and for the prompts we get to the point. We usually, what we do is we're prompting with a context. We're saying that the model should keep in mind that it is a prominent competitive programmer and it's invited for a programming competition and you're given task to solve. And here we have some description that we want the input to be from a file, and after that we are giving usually the description of the task, which is from up here. And before that, let's have a fast read of what the task is. As you leave the cave, so far we are in a submarine in the ocean, and we were hiding in a cave, and we were navigating how to go out of the cave, how to not break our submarine or hitting some too warm parts of the cave, etc. That were some of the tasks that we've been solving, and now we are leaving the cave and reach open waters. You receive a transmission from the elves back on the ship. That's our ship that is helping us to navigate. The transmission was sent using PNC interchange transmission system, a method of packing numeric expression into binary sequences. Okay, and your submarine computer has saved the transmission in hexadecimals, your puzzle input. We have that as hexadecimals. The first step is of decoding the message is to convert the hexadecimal representation into binary. Each character of hexadecimals corresponds to 4 bits of a binary data. Okay, we have 0 up to F capital, and we need to decode that. And the bit transmission contains a single packet at its outermost layer, which itself contains many other packets. The hexadecimal representation of this packet might encode a few extra 0 bits, okay, at the end. That's padding at the end. They are not part of the transmission and should be ignored. For example, here we need to chop it 4 by 4 and see in which moment actually probably the last 4 are ending here, and after that we have these 3 padding bits. Every packet begins with standard header. The first 3 bits encode packet version, okay, and the next 3 bits encode the packet type, ID. These 2 values are number. All number encoded in any packet are represented as binary with the most significant bit first. For example, a version of encoding as the binary sequence 100 represents the number 4. It's from here, the encoding. Packets with type ID 4 represent a literal value. Literal values packets encode a single binary number. To do this, the binary number is padded with leading zeros until its length is multiple of 4 bits. And then it is broken into a group of 4 bits. Okay, we have padding with leading zeros. For example, as here we'll have 0, 1, 0, 0, and then we have had it is multiple 4 bits, or 1 4 bits, it's this number with padding. Each group is prefixed by 1 bit except the last group, which is prefixed by 0 bit. This group of 5 bits immediately follow packet's header. For example, the hexadecimal string becomes each bit is a label indicating its purpose. Okay, we have for each bit our package version 6, our package type ID 4, which means the package is literal value, bits label A, start with 1, not the last group, keep reading, and the content the first 4 bits of the number. And 5-bit label starts with 0, not the last, and we continue, and contains the following bits of the number. The 5 bits label C starts with 0, which means that's the end, and contains the last 4 bits of the number. 3 unlabeled bits at the end are extra due to the hexadecimal representation and should be ignored. Okay, we cut that one. Okay, so far more or less clear. I think we need to get from the hexadecimals firstly to this byte interpretation, and after that going through and see which one is corresponding to what when it's the ending sequence, and after that, after we see this sequence, we know that if there is after this 4 something following, we should ignore it. Okay, the 3. So this package represents a literal value with binary representation, which is 2021 in decimal. Okay, every other type of package, any package with type ID other than 4 represent an operator that performs some calculation on one or more sub-packets containing within. Right now, the specific operations aren't important. Focus on parsing the hierarchy of sub-packets. The operator packets contain one or more packets. To indicate with the subsequent binary data represents its sub-package, an operator packets can use one of two modes, indicated by the bit immediately after the packet header. This is called length type ID. A second, I didn't get that. An operator packet contains one or more packets. Okay, I'm an operator packet, which means that my type ID is not 4. To indicate which subsequential binary data represent its sub-packets, the operator packets can use one of two modes, indicated by bit immediately after the packet header. Okay, I'm reading this packet header, and after that I have one bit that it's telling me what are the sub-packets. This called length type ID. If the length type ID is 0, then the next 15 bits are number that represent the total length in bits, okay, of the sub-packet contained by this packet. If the length type ID is 1, then the next 11 bits are number that represent the number of sub-packets immediately contained by this packet. Finally, after length type ID bit and the 15 or 11 bits field, the sub-packet appears. For example, there is an operator packet string with length ID that contains two sub-packets. The 3 bits label are saying, okay, that's our package version. Here the type ID is saying, okay, we're type 6, which means the packet is an operator because it's not 4. The bit labeled I is the length type ID, which indicates that length is 15 because it's 0 bits and we're counting 15 bits contain the length of the sub-packages in bits, and here there are 27 bits. The 11 bits label A contain the first sub-packet literally value representing the number 10, and the 16 bits label B contain the second sub-packet literal value representing the number 20. After reading sub-packets, the total length indicated in is reached. So parsing this packet stops. Another example here is operator packet with length type ID1 that contains 3 sub-packets. Here it's 1, it's 11 bits and so on. We're reading them. What's our task? After reading 3 complete sub-packets, the number of sub-packets indicated in L is reached, and so parsing of this packet stops. For now, parse the hierarchy of packets throughout the transmission and add up all the version numbers. Okay, we need to simply get this version 7, version 1 and so on, and we need to add this number. here is example, few more example of hexadecimal encoding transmissions. Decimal is 16, decimal is 12, decimal is 23. Okay, I need simply to get this 8, 6, and so on. I need to get their versions. So to say once I have a packet version 4 which contains operator packs, etc. I need to sum up all of them. Okay, let me see what's my input. Brilliant. I'm getting here. That's my final input. Let me save it here. And in my test input, let's start with something easy and simply have, do I have hexadecimal example of the pack? Actually seems to not have that. Or no, I have. Let me start with this one because that's the easiest example, and I would need, when I have only this one, I will need to get 16 to verify my okay, let's go here. I have this one. I want to see how big is this token. Quite massive, but let's proceed with it. I think in this case we might not really want to read from the file because it's our message is, so to say, not so big. To solve the given task, we will follow these steps. We firstly read the file. That's a little bit, especially in this case, a bit redundant, but we can change that eventually if we have a problem with the size of the program, because one of the restrictions that currently we might run to is that ChatGPT and GPT-4 specifically doesn't have enough tokens, and probably reading this file and so on might cause some issues. Okay, I'm seeing here parsing the packages and so on. That seems promising. Now we're checking for the type ID, if it's this or this, etc. We're checking if it's 1. We're adding 5. Shouldn't it be 11? Always adding, and plus 4. Anyway, we're having this packaging and so on. I'm not super sold on the packaging. I think that part of the logic is more or less correct, but we will need to iterate. Okay, it's reading the file at once. It's trimming the space and so on. That's very good. It's one line. And it's reading the input. Okay, let's grab this one. This is not as complicated as program as I would expect. Okay, we're having some issues. Let's try to debug line by line. Here the first part is we read the data correctly and we get the hexadecimal string without any spaces and stuff like that. Printf, why I want printf? Because I want to have it like that to make sure there are no empty space and all this stuff. Let me clean it. Okay, that's everything seems to be right correctly. Up to that point we're okay. Let me see if we get it to a binary string, because here I want to see if the binary is correct. It seems more or less correct. Let's double check the logic. We start parse a string. We have it to unit. We are saying the base from which it's 16. Okay. Bit size is 8. And we're getting as an output uint, and we're making from the uint a binary. Okay, that's probably look legit, but let me try to do 44. I will expect here, let me run it again, zero, zero. That's exactly what here we should get for 4. Okay, it seems, let me try again 4f, for example, 4f, okay, and I think we're okay for the this part of the parsing. The logic seems correct. let me close previous days. Here we have the base 16. We're saying okay, we're working with 8 bits, and here we have this let's ask Bing to simply explain to us what does do. In my Go program, I have the following code. What does it do? Of course, we need chat and we need the precise one, not to let's add our prompt to Bing. We ask Bing that, does eventually the Bing answer. Again, as always, we keep out that simply to have our total info. Formats the value as binary string with at least 4 digits, leading zeros if necessary. Okay, that's saying okay, I want to be at least 4 digits, and we put zeros if there is a empty space because it's 1 for example 3, and we put zeros in such cases. Okay, it's this 0, it's simply to here we have we're saying to be at least 4 digits, and we are saying here to put leading zeros if it's less, if it's 1 and so on, which is exactly what we want. Yeah, it is absolutely perfect. Let me grab these bad boys. Somehow, yeah, it's a bit sad that I couldn't copy and paste these numbers. When we look at the Go program, when we are here, okay, let's go to the meaty details, because here the main part of the logic. Up to that point we are all okay. It seems the bin string is fine, and we want to see here what's happened when we run it with actually the test input, what's happening in our parsing, because on line 22 we are trying to index something that is exceeding our length of our string, or what we have here. Okay, we have our parse packet and we start with 0. Yeah, that's fine. In this packet we are getting the version. Okay, let's see for that part with the version. Here, that's our test input. We have a operator packet that the version is 4, which contains operator packet version 1, which contains operator packet version 5, and literal value version 6. Okay, in our case here, that means that print when our version should be 41560 4156, and here the 0 is because we probably don't cut our binary string input. I mean, here, if we came at the beginning of the function, not sure we're calling it recursively to parse all the packages. And so on. But if we get here, let's do it the step before that. Here we have our not here, in our main function we have our binary representation here, empty print wine, and we have our binary string. We want this binary string, we need to see what is its length. Let me double check. The length is 72 characters. If we try to divide by 4, we'll see that there is a reminder. Is there? Okay, 72 divided by 4. How long is this? 18. I was expecting that we have some padding, like extra padding, and we are simply not removing it. But in this specific case, that doesn't seem to be the case. At least if we do that and after that multiply by 4 and we make sure that they're equal, we'll get true. Okay, in this case that's the false alarm. I was thinking that here we need to do stuff like having our then string and simply getting it up to the point what's the leftover we have the length, we are removing all the one that are left over, but in that case that will not change anything. However, let's keep it like that. That's simply to trim the not needed trim not needed 0 bits at the end. Again, in this case I don't think that we need that, but okay, let's see how the parsing is going step by step. Here we have the version and the type. Let's we have for true the type it's 2, operator, contain operator, and we have the version 6 is literal, yeah, which is 4. All of that seems absolutely exactly what would we expect. However, here we get to the point before to crash. We have this following we have in our case index that has 69. We're able to do this operation, but not that part here, because in that case we're at the end of the package. And let's see how we identified that this stuff is actually the end of the package, because we do all of this stuff, but actually we want to see where is this check that you know, we're on this code, and this code starts we need to see, let me see, okay, let's do it with this one because we can actually debug it here. Haven't seen that we actually have this one, and we can debug the actual binary value. Okay, for this one we are getting version 14, which is okay, we have version 7, we have 1, 2, 3 sub-packets. Which version are they? Contain the number of sub-packets. There are 3. Okay, here we stop. Let's firstly see. Here we don't crash, and we have 7, after that 4 and 1 like version. Everything is working perfectly fine, but why would it where it's counting the number of packages that we're now here. Okay, we have the sub packets length and so on. 1 second, let's move there, because here we have these indices. For this example, they seems to be all working perfectly fine. Let's see when we are getting the length type ID. To get the length type ID, we first check are we are type 4 right here, and if we are type 4, we are checking, okay, are we here type ID, we're checking the type ID. If the length of type ID is 0, then the next 15 bits are numbers that represent the total length. I think this bottom of the recursion, because okay, we have 6 already here. If we go here, we will get 11, and if we are with 1, we will get another another 5. That was big time false. Let me the only time that we're going here version and so on, length ID. Do I have another hexadecimal? I want to Okay, let's start with this, the easiest one, because I think we should go step by step. And let's see this one if it's working correctly, where is getting the version. In our case we should end up like that, and let's see if my cutting efforts kept the stuff okay. fmt print line. Okay, that seems to have no real effect here. The end of the demo, we can get rid of it if it's meaningless. I was thinking that will allow us to cut this meaningless stuff, but it seems like we always have it. I mean, I'm not sure about that. I think that further on we might want to add it. Anyway, this one seems so far legit. Let's go step by step. We have it here, and we run the code, or actually if we try to debug it, run debug, probably will crash because of the file. Yeah, I cannot find this file. From here, but if we try it, okay, now we're with the entire string, and we're stepping in. We're with version 6, and here we can see we're version 6. Below BT's label indicates its purpose. How we get these bits? Let's again ask what is this doing, because here we get the bit and we could you explain to me what this code in Go is doing? Give me an example. Subtract the character 0 from the cover and integer value. Then shift left by 2 bits. For example, if bit string is 0011, that the ID is 2, we'll get 1. We'll subtract 0 is 1, shift left by 2 bits gives 4. So the result expression would be 4. Yeah, for me it's interesting how this one is working. Now we are getting okay, we're shifting to our what is this then doing? This code takes 3 characters from the string. We have our, for example, if the string is shift this left or okay, bit or is saying okay, now that's the bit that if I'm here 1, option for 2, for 4 and so on, and I'm summing them up with this OR. But when I'm reading only the first 3 bits, is that correct? Below each bit indicates its purpose. Okay, the first 3 bits are saying me the version. The following 3 bits are indicating the type ID. Okay, that's 3, 4, 5. Okay, that's all looks absolutely fine. I can understand why is that. After that we're adding 6, which I again understand because we operate up to here with 6. I'm going down, checking mine type ID is 4, my version is 6, and I'm adding to my index whatever I've been doing here. Okay, perfectly fine. I like that. The 5 bits labeled A start with a 1, not the last group. Okay, after this 6, so to say here my index is 6, which means on position 7. Here I'm checking if I'm 1 or I'm 0. Whenever I'm 0, I know that's the end. Okay, how I check if that's the length? Actually, I'm not sure. Here I'm checking, okay, am I type 4? Yes, I am. I'm checking, do I have my following bit being is 0 or 1. I think in this case, where on earth I'm checking if I'm AND 1 or 0 here for this index. Somewhere I should check if I'm 1 or 0. Okay, I do this checkup here because I'm checking if I'm type 4. Let me see what I do when I'm let me see what I'm doing when I'm a package 4. Okay, package with type ID4 represent a literal value. Literal value packages encode a single binary number. To do this, the binary number is padded with leading 0 until its length is a multiple of 4 bits, and then it is broken into group of 4 bits. Each group is prefixed by 1 byte except the last group, which prefixed by 0 byte. This group of 5 bytes immediately follow the package header. Okay, we have these bits that are the type ID and the version. After that we have this value that you think, okay, here is the number, that's not the end. Keep this 1, after that keep eventually this one, and keep this one, and make one number with, and then return it. Okay, how is that being done in this case? I'm simply checking. Okay, now I'm type 4, which means that I'm in this kind of a loop. I'm checking, am I 1? If I'm a 1, I'm saying, okay, I will move 5 more bits. And after that I've moved 5 more. But that looks quite wrong to me. I'm getting the version and getting then the index. Let me check this stuff. I'm here, I make that. That's for loop. Oh, that makes sense. I'm adding all of these values. I was thinking that's if condition. I'm continuing and adding that up to the end when I see 0. That's absolutely correct. Oh, fantastic. Now I'm in position 16. I encounter 0. And I'm grabbing this 5 here and ignoring this stuff from here, and I'm at that position. I'm returning here the function. It's returning in that case the version soon, and here I will have the last index where the number ends. Okay, in this case it's 6, and I'm returning 21 because it's such a package. Okay, I have the sum completely fine. I think this part of the logic works perfectly fine. That was doing it with the package, with this package. For that, here we are not really parsing the number. In my opinion, here we should return the value. Instead of having this index and moving so, we should have here the number and parse it and doing the cutting, but I would imagine that we'll need to do that in the second part. Now we're out of this one and we want to check with another one that it's actually that it's not 4. It's not looping through a number, and it's leaving every other type of packet, any packet with a type ID other than 4 represent an operator that performs some calculation on one or more sub-packets contained within. Right now, the specific operations aren't important. Focus on parsing the hierarchy of sub-packets. The operator's packets contains one or more packets. To indicate which subsequent binary data represents its sub-packets, an operator packet can use one of two modes indicating the bit immediately after the packet header. Okay, an operator packet, that's any packet that is not 4. Let's grab this one, which is exactly example of such a packet. Can put it in our input. And if we run our program, or so to say debug our program, we are here, we are at the beginning, our version is 1, we're fine with that, our type is 6. Let me go to here, we have a package version 1 and our type is 6. After we read these two, we need to check, we are making the shift of 6 and we are checking what's our type. In this case our type is not 4, we skip that. We came to here, we're printing to the standard output, blah blah blah, we don't care for that, we return. Now we are looking at the index 6, which is this one, and we are checking a bit label I, 0 is the length type ID, which indicates that the length is 15 bits or 11 bits. In our case that's 0, and that's convert. We need to check, is that 0? If that's 0, that will mean that our length found from here, it's 15 bits. If it's not, we can see if it's not, it's 11. Okay, we need to have the number of these subpackets and their subpack length. I would imagine that here will be some mistake. Okay, here because we check this I, we're increasing the index and we're moving forward. We're redefining that. We're checking, okay, our length is 0 exactly. From here we're going to the subpack length, but how we determine this subpack length? We have this 0, which tells us that our length is 15 bits. What we do here is we're reading this here is getting not clear to me. We know that our indicates that the length is 15, representing the number of bits in the subpackets. Each subpacket is 15 bits. The 15 bits label L contain the length of the subpackets in bits 27. Okay, here we start with 0, but we actually go to this one and evaluating of the length bit by bit. Here we need to get 27, and we're doing it with going through the iteration hop. Here we have 0, and here the whole index 7 we also get 0. If we move our length continuing to be 0, we move again, we move further and further. After having like 7, 8 zeros for an index 14, it's still 0, but in this somewhere here we should get our first 0. Is that correctly? Okay, we get 1. We're on our first one here, and we need to go we need to have this number actually convert to this binary number, convert to a decimal number. Could you convert this binary number to decimal? Okay, let's see. Here we need to have we have 16, we have 18, we have 0, after that we have 2, and we have 1, 27. And how we do that, it's every time when we have 1, we're shifting and shifting and shifting here in this implementation, and we are making XOR with the actual integer. Okay, let's me see 3, 6, because it's 13, 27. Now we are going out and we're continuing with this version sum. In our case, the version so far it's 1. We're checking, is the subpackage length 0 and length type ID, like what's our length type ID? It's 0. We're checking if we're 0 length type ID and the subpack length is 0, then we break, because this length check after that we check if the length type ID is 1 and number subpacks is 0. Okay, that's in this type we have this subpack length, and in the other case with 11 we actually have completely different thing. Here we have length type when it's 0, that it's saying okay, are the number of represents the total length in bits of the subpackets containing these packets. Okay, now we know that our total length is 27, and when it's 1, then the next 11 bits are a number that represent the number of subpackets immediately contained. Okay, that will make absolute sense, because they're saying okay, that's 0, we have not much here. When we go here, we don't we're going to these subversions. We had the versions from the first one. In here we simply dig inside, we have this ID X, which it's at that stage it's on this point, it has the first 6, after that 7, had this 15, it's 22, plus, and it starts from 0, it's exactly 22. Okay, that we now go in to see what about the following packages. Because here we have packet version is 1, and after that we have this 27. We have a bits label A contains the first subpack, literal value representing the number 10, and the second is 20. Okay, if we go through, we go in this and we check what on earth is that. That's version 6. What's the type of that? The type is 4, which is the literal. We go here, we get in, we have the literal probably jumping on, we have the 6. For the 6 we are adding it to here, and we are changing the index to the new index. After reading it, a second, the new index is 33, which is 22 plus 11. After that we add this sum. We're checking length type ID. Is this 0? If it's 0, we're having our new minus the ID. One second. Because here we have this subpacked length, and we want from this length to remove as much as we write, but with this one here we want to have 33 minus, but before to have this change of the index, this one that it's simply saying okay, now that's 33. I think that's the mistake here. This part of the logic needs to be done here. We need to have, that's my guess. I think simply how we were subtracting here was wrong. Let me remove this breakpoint and let me I simply run like that. Now that's like the entire project. I need to have it like the 16 part 11. Okay, fine. We are getting 9. We are getting 1. And for this we are getting 4. 4. Yeah, that's 9. Okay, so far I think that actually that's more or less the correct logic. Let me try with the actual input. We're getting 9 4 3. Okay, that's solve our task for day 1. Let me simply delete the print and see how it's running. Okay, perfectly fine. Let's see how will be part 2. I expect to get a bit harder. Thank you for your time and see you in the next video.